let us say that there are also other functions that are implemented in the K5O implementation. And some of these are, for example, K5O len, K5O avail, K5O size. And I would like you to go through the file and basically figure out what do these three lost calls do. Now we are done with the queues. Let's talk about the maps. And many of you might be well aware of what a map is. And maps are basically it's basically a data structure that maps a key to a value. And hash tables are a type of a map, but not all maps are implemented as via hash tables or via hashes basically. Linux actually has an implementation for maps. It's not general purpose. It is there for just one single purpose and one single functionality, and that is basically mapping a unique identification number UID to a pointer. It's pretty efficient, pretty simple. It might be something to look at for your project. I'm not saying that it is the best, but it will provide you with very basic functionality. Now, there are three operations that come with the map. The first one is to add, which basically adds a new uh, keyem value. You can it's The add function is piggybacked such that with an allocate operation on top of the add operation, and the allocate operation basically not only adds UID value pair to the map but also generates the UID. So you can even use it to generate new UIDs for your keys. You have a remove, which removes the key, and you have a lookup that basically brings you the value. Uh, you can actually read more about IDR and the ID management in this link, in this article that explains how does that work. Let's talk now about trees, and we're going to spend some time on this. And a tree data structure. I mean, most of you would have heard about the binary trees. I hope binary search trees basically. And in tree data structure, you basically have a root node, and you have children on the left, children on the right, and leaves towards the end. And a binary search tree will actually have it such that on the left hand side of any node there exists only nodes with lower values, and on the right hand side there exists only nodes with higher values. So for example, you have a 3 here, you cannot have any numbers except 1 and 2 over here, but here you can have anything that is above 3. But since you have a 7 here, then you cannot have anything that is you can only have values between 3 and 7 over here. Otherwise, your left hand side will contain numbers that are larger than your right hand side. Then your right hand side here will only contain values that are larger than the numbers that you have. So you can have anything 7 of 7 and above. And you basically can have like 9, 17, but then 17 will have on the left everything that is lower. And then you would try to balance the tree so that you can basically have, for example, the yeah you can the whole idea is of binary search trees is that you try to have them balanced as much as you can. And a self-balancing binary search tree will look something like this, and you will basically not have a lot of dangling nodes. I mean, you'll not have